Hello and welcome to T3 Day 11 of Honors Precalculus. We're going to be graphing conics in polar form. The key here is to take what they give you and draw out as much as you can of what's been given to you first to help you out figure this out, because really it's just filling in the blanks on 4 different possible equations. So it says find a polar equation of an ellipse with a focus at the pole, so the pole is the origin, and vertices of these 2 coordinates. Keep in mind that these are polar, right? So 5 pi over 2 means an angle of pi over 2, which is the positive y-axis, and 5 up. So it's pi over 2 from there, and it's 5 all the way up to here. So that's our first vertice right there. That's our first vertice. And then 3 pi over 2. 3 pi over 2 is here, and it's a distance of 1. So it's going to be here and here. So if we have an equation, if we have these as vertices, so it's -1, our ellipse is going to look something like this. It's going to go like this. It's going like that. Now we don't know how wide it is, but that's what we're going to figure out. But we know it's going up and down because the focus is here, so that means the other focus has to be right there. So it's going up and down. Because it's going up and down, we know it's going to be EK 1 over, so 1 minus or plus E sine of theta. So the directrix here, because the focus is here, the directrix is going to be down here. It's going to be below, so therefore it's going to be minus. What we now know is we have 2 points that we can work with. We know that when r is 5, you end up with EK 1 minus E sine of pi over 2. And then the other one we know is when r is 1, we get EK over 1 minus E sine of 3 pi over 2. And this is where you just need to remember your basic trig. When you simplify this, you end up with EK over 1 minus E. And here you end up with EK over 1 plus E, because you just do basic trig. So you need to remember what these trig values are right here. So when you multiply this out, it's very similar to what we did before. We cross multiply. 5 minus 5E is equal to EK. And over here we have 1 plus E is equal to EK. So what we can do here is set them equal to each other. 5 minus 5E equals 1 plus E. So we end up with 4 is equal to 6E. So E is equal to 4 over 6, which is 2/3. So then we can solve for K if we want to. We can plug it in. You can take this value right here and you can plug it in. So you end up with 1 plus 2/3 is equal to EK. Which you can do 2/3, but it's going to be 5 over 3 is equal to EK, which is really what we need on top. We don't have to solve for K on this. It doesn't ask us to. So we know now that EK is equal to 5/3, which is right there. So now we know that R is equal to 5/3 over 1 minus, because we know the E value is 2/3 right here. We got 2/3 right there. So there's our 2/3, and it's sine of theta. We're going to clean this up a little bit, and we're just going to multiply this by 3 over 3. And if you do that, you're multiplying by 1, which is totally fine, and you end up with r is equal to 5 over 3 minus 2 sine theta. It flattens it out a little bit. We want to get rid of the compound fractions. So that would be the equation we want right there. So let's see if we can graph this without a graphing calculator. And we're going to find the directrix and all the vertices in both polar and Cartesian. So the first thing is, this is not 1, so we need to turn it into 1. And we're going to do that by multiplying the top and bottom by 1/5. So we have 1/5 and 1/5. When we do that out, we end up with 21 over 5 over 1 minus 2 over 5 cosine theta. That tells us that E is equal to 2/5, which is less than 1. So therefore, which is that 3 dots, it means therefore this is an ellipse right here. Nice. What we can then do is plot some points. When theta is equal to 0, so when it's on the x-axis, r is going to equal to 21 over 5 minus 2 cosine 0, which is equal to 21 over 5 minus 5 minus 2. Let me put that right under there so it's a little bit cleaner. So that's 21 over 3, which is 7. So that means we have the point 7 when this is theta right there. So that point right there is 7 comma theta value of 0. So then let's also do, let's do theta is equal to pi. It's just a nice one to plug in. So r is equal to 21 over 5 minus 2 cosine of pi. Cosine of pi is -1, so you end up with 21 over 7 this time, which is 3. In this case, though, remember it's the distance. It's the distance. And we know that this is negative right there. So our directrix, in this case, we have to be very careful about this. but we can plot this point right here as the distance when its theta value is pi. So theta value of pi is that whole direction. So 3 is going to be a distance of 3 right there. So we have this and this, and we have our decent ellipse. So we know there's going to be an ellipse, something like this. We just don't know how high it's going to go. So what we can do now is solve for our k. So we do that because we know that the e value is 2/5. So what do we know here? We know that e times k is equal to 21 over 5, which is this value. That is e times k. We know that e is equal to 2/5 right here, 2/5. We get it from right there. So we end up with 2/5 k is equal to 21 over 5. So this tells us that k is equal to 10.5. But because this is a minus sign, the directrix will be at negative 10/5. So the directrix is going to be x is equal to negative 10.5, excuse me. So we have those two vertices, which allows us to find the center. So what's halfway in between here? So we have negative 3 right here, we have 7 right there, so we add 5, so it's actually going to be at a little bit further out is 7, I actually realized here. So this should be at 7. I labeled it but didn't graph the right one. So 7 is right here. What's the center? The center, if this is 7, 0 right there, is going to be here at 2, because that's halfway between negative 3 and 7. So that's our center right there. So what does that tell us? Well, we know the eccentricity of an ellipse is c over a. So we know the eccentricity, and this is 2/5 already. So that's going to be c over, well, we know this distance right here is 5 right there. So that tells us that 5c is equal to 10, so c is equal to 2. We also know, because it's an ellipse, that c squared is equal to a squared minus b squared. So we know that 4 is equal to 25 minus b squared. So that tells us that b squared is going to equal to 21. So what that means we now have is we have the center is there, over, we know that's squared, over 5 squared, so it's 25, and then it's b squared, which you already know is 21. So b is square root of 21, but when we write this out, we can just say that. So it's y squared because it's on the x-axis, over 21 is equal to 1. So what that means is we go up roughly the square root of 21. Square root of 21 is a little more than 4. So we're going to go up to like here and down to like here. So what does our ellipse actually look like? It looks like this right here. Here's our ellipse right here. Not drawn very smoothly. So when we do the vertices here, we can plot them out in polar, and we can do Cartesian. So this right here is our first one. So what are our vertices? This is the key thing. And remember, when we do vertices, we're looking for them in polar, and we're looking for them in Cartesian. Cartesian right here. So in Cartesian form, we know that this point right here is actually this is 7, 0. And we actually know that this point right here is 3, 0. That first point is the same. It has an angle measure of 0 and a distance, so it's the same in polar and Cartesian. But this one right here is going to be 3 comma pi, because it's pi rotation. This is 3 comma pi. So when you do these out, you know that this one in Cartesian is going to be, it's over 2 and then up root 21. So it's over 2 and up root 21. And this one is over 2 and down root 21. That's this one right here. So that's 2 comma negative root 21. And then we use our conversion to find that this is 5 comma 1.159. And this one is 5 comma negative 1.159. And what you use to do that is, you know that r squared is equal to x squared plus y squared. And we know that theta is equal to tan inverse of y over x. Those are the formulas you use to find those values. So let's graph this one and also state all the intercepts in both Cartesian and polar. So the first thing we need to do, remember, is this has to be 1. So let's divide the top and bottom by 4, and we end up with r is equal to 12 over 4, which is 3, 1 plus sine of theta. It's kind of nice. It cleans up nicely. So this means that e here is equal to 1. E is equal to 1 in this case because that's what the coefficient is here, right in front of sine. So that means this is a circle. We haven't done that yet. That's kind of nice. Oh, excuse me, it's equal to 1, excuse me. So it's not equal to a circle, it's equal to a parabola. Parabola, I gotta remember that. So it's equal to a parabola. So how do we do this? Well, we know that EK is equal to the top value of 3 right there. We know that E is 1, so this means K is equal to 3. Okay, so K is equal to 3 and it's plus, so that means the directrix is gonna be at Y. Directrix means it's gonna be Y is equal to 3 because it's a plus sign right there. So here's our directrix at y equals 3, like this, and it's a parabola. And again, our foci is always there. There's our foci. It's always at the origin, just for reference here. So then what we can then do is we can find intercepts. So we know that this thing is going to go down, because if that's the foci, it's going to roughly do something like this. I'm just being very rough about it. So what we can do is if we find the intercepts here, it's really helpful because our vertice right here, there's our vertex right there. Our vertex for this parabola is also going to be on the positive y-axis, and that's when you have pi over 2. So the question is, what happens when you have r of pi over 2? Well, that's 3 over 1 plus sine of pi over 2. So what's that going to be? That's just going to be 3 over 1 plus 1, which is 3 over 2. So that point right there, it's a little bit lower. It turns out to be 1.5. So when we graph this, it turns out that this is 1.5 right there. So that point right there is 1.5 comma pi, and that's in polar form. And it's going to go down like this. So we could actually find the other intercepts, but remember that's in polar. If we wanted this in Cartesian, it would be 0 comma 1.5, because that's the x value and then the y value. X and y, it's Cartesian right there. The next thing we need to find are these y-intercepts. The x-intercepts. The x-intercept is when we're at 0. So this is 0 degrees right there. That's 0 degrees. So r of 0 degrees is 3 over 1 plus sine of 0. Well, that's 0, so that's going to be 3 over 1, which is 3. So these are actually right there. 0 degrees is going to be 3. And because it's symmetric, we can just do the other side over here. It's also going to be 3 when it's at pi. When it's at pi right there. So what you can say right here is that you want the vertex, as we said up there, and that in polar, it's up there, it's going to be 1.5 comma pi, but in Cartesian, it's going to be 0 comma 1.5. That's this point right there, the x-intercept, which is also, so the y-intercept, which is also the vertex, which is also the y-intercept. There's one of them. The other thing you need, though, is the x-intercepts. The x-intercepts, and this is when y is 0, those polar forms are 3, 0, and 3 pi. Those are these points right here and right here. So what are those in Cartesian? Well, it's the same here. Anything on the positive x-axis is the same. And this one is -3, 0. So you need to be able to convert between the two. But remember, just recognize the right form, and you should be good to go.